The title of this paper is Coordination Among Neural Modules Through a Shared Global Workspace, and it was published in ICLR 2022 by Binjo's team. So this paper tries to propose a model that can assist coordination between different neural modules using a famous theory, so-called global workspace theorem. Uh, in the next slide, we'll present the paper and discuss its advantages and also limitation and provide our tested solution for one of its limitations. Based on the recent models and research in the area of deep learning, we can see its movement from a less structured state to a more structured state. For example, transformers segment test data by their position and then try to find pairwise connection between them using self-attention, or object-centric architectures decompose images into entities, or vision transformers segment by patching. So what's the problem in these models? Interactions between different elements are modeled via pairwise interactions. For example, transformers uses self-attentions and graph neural networks are employed by object-centric architectures to represent connections between entities. So how we can change the pairwise interactions to a global coordination and interaction between different elements. So in the next slide, we provide a solution for this limitation. In 2005, Bars elaborated more about his idea of global workspace theory. Based on this theorem, the brain consists of specialized components that perform specific functions and communicate with each other through a shared communication channel. And this channel has a limited bandwidth, which means that only a limited amount of information can pass through it. So, making it necessary that only the most informative information can pass through it. This figure explains the whole idea of global workspace theorem, where modules or specialists are supposed to collaborate for solving a task. So the task is processing an input image, and this process is explained in these steps. In step 1, which the leftmost image representing it, several specialists become activated and process the input. Then, in step 2, the activated specialist gets right to write their finding into a shared global workspace. And finally, in step 3, the global workspace broadcasts to all specialists to let them know about its recent updates. In other words, the shared global workspace provides a channel to inform specialists about each other and make them connected. So now we can ask this question: why do we need to GWT into AI domain? There are three benefits. At first, it helps to bring the distributed computation into AI domain. When we have several specialists which can work independently, then we have scaling property to add more specialists. The system robustness will be increased as the system can tolerate the loss of one specialist and still continue working. Moreover, the specialist can communicate efficiently because they don't need to communicate with each other and therefore reduces the communication cost. Number two, the system benefits from a coherence through the shared workspace, which further helps the specialist to benefit from each other. And finally, we can look at shared workspace as a necessity if we want to have a common representation between different data modalities and latent spaces. For example, the image and text models can leverage into a same representation through the global workspace. In this slide, we try to show how a global workspace can be applied in different neural architectures. At the first row, this row, we can see the original architectures, and in the second row, this one, we can see how global workspace changed the architectures. For example, in the second column, in this column, we can see how it changes the transformers architectures. In the original transformers, all the information from one layer passes through the layer using the self-attention procedure. So it's shown by a fully connected network. However, using the global workspace model, only several pieces of information can write into the shared workspace, and then the shared workspace will decide how to update the flow of information. The same restriction can be found in other architectures as well.
Thank you, Salman. My name is Hossein, and I continue the rest of this presentation. So now we are in proposed method slides. As you can see here, I try to split down the whole process of the method proposed by the paper in three steps. As Salman mentioned, we have some data or like information. Let's say that they are information. We have some mechanism. They can read the information and provide their feedback, and also we have a shared memory. So the first steps, actually the mechanism, they try actually to give the right, they somehow try to compete to be selected actually to update the workspace. In the second step, the selected mechanism, which I will explain what are exactly those mechanisms in one real world scenario. These mechanism, they try actually to write their information into the shared workspace, but only those that are selected actually can write their information. Now in the third step, when the workspace is updated, then it tries to bring all the information back to all mechanism, let them know about what happened just inside of the workspace, what information added, what was the main change of this information. So this is the three steps that I am going to explain each one of them one by one in the next slides. So before talking about the steps of the proposed method, let's provide some notations. We talk about transformers in this notations. So let's say that we have some data x represented by x. These data are like number of tokens in text and the vocabulary size. Then it goes to some positional embedding and embedding functions, and to give us the very initialized embedding space of data, and we represented the layer number by L. So let's say that we are in layer L. The input to this layer comes from previous layer. So as you can see here, HL minus 1 goes to one layer of transformers, and then we have H of L. It is in dimensionality of T, number of tokens, by D, which is the embedding size. For example, in birth base, this one is 512. We also introduce N of B as the number of entities or mechanism or specialists that we talked about in previous slide. We also shows the state of that mechanism by HLK. So HLK shows the state of a mechanism K in layer L of transformer, and it is in dimensionality of number of tokens T to N of H, which is actually the representation size for each mechanism. To give a concrete idea, let's say that we set the embedding size as 10, and I want number of mechanism to be 5. So this division gives us the n of h, which is 2. Like each mechanism has 2 entries. So to take the mechanism K, for example, let's say that this one is mechanism K. It has only it has all the rows of H, but only two columns of that. For example, the first two column is for H1, the second two column for H2, and so on, so forth. And for example, this, if I take this out, this would be the mechanism tree for this setting. And finally, the memory is gonna be represented by a matrix. So this matrix has several rows. Each rows has dimensionality of 512, for example, in this setting, or in general D. And the number of slots or number of memory is equal to n of m, which is the memory size. Okay, so to see how the mechanism can compete with each other to get the access of write into the shared workspace, let's start from one layer. Let's say that the input of layer L, which is HL minus 1. To find the importance of each mechanism, we actually simple. We multiply that mechanism representation to a new set of parameters, and these parameters are going to learn during the training. So let's say that, as we explained in the previous slide, the size of mechanism is T times n of H, and n of H is actually comes from this division. And the new weights here parameters is n of h by 1. So C of k is actually lives in a space of t, number of tokens, times 1. And after this multiplication, like a dot product, then we concatenate all of these vectors by each mechanism, and then we do a softmax. So this gives us a matrix of this size, which actually shows how important are each mechanism for this particular input. So after that, we want to select the best mechanism. So to do that, we follow the strategy of taking the top k. So f of t here shows the index of those mechanisms that are inside of the top k. And then we take, for example, let's say that for mechanism number k, we got this vector, and this vector is t by 1. T is number of tokens times 1, and each one is the importance for each token. So 1, let's say 0.2, and so on and so forth. Then if this mechanism is selected by after doing softmax and taking the maximum, then all these values are gonna multiply to the actually, let's say that this is let's say this is k, mechanism k, just for simplicity, and then this one is selected. So we multiply all these two entries by 0.1, this 2 by 0.2, and so on and so forth for other entries. And then this mechanism which is selected are going to be multiplied by its weight. But we see this one in the actually next slide. But this strategy, we just select which of these mechanism like are belong to top k or not. Okay, in step 2, which is consists of two parts, the first part is selected mechanisms first try to update their hidden state, and then they write on the workspace. So how they update their state, it's simple. First we save their residual as the current state, and then we pointwise multiplication between the importance that we computed in previous slide by a self-attention of that state. And this self-attention is like qk transpose, so we by from transformers, and then added by residual. So now this is the updated state of that mechanism k, and then we go for the second step to update the shared workspace. To do that, we first introduce a new representation of a, which is actually a concatenation of a1 to a and b. And what is a1 to a and b? It is actually a pointwise multiplication of the importance of that mechanism to its representation. So this concatenation is applied in the second step here. So first we make a query tilde by multiplying memory to W, which this W is another set of new parameters. Then we have Q tilde. So then first we multiply A by a new set of parameters V to find A, and these A are gonna concatenate it by M to form R. Then we go for doing another set of self-attention between memory this time and parameters we have. So to do that, first we need a Q, right? In self-attention, we always need the QK V transpose, QK transpose V. So this one is actually V, which is R times to another new set of parameters represented by tilde here. Then we have query, which we computed above, and then we need a key. To do that, we multiply R by another set of parameters, and R comes from previous step. So this is again another set of QK transpose V, but this time is for memory. And then memory attend itself, added by new information from the input. Then we get a new updated memory for this round. Okay, in step 3, now it's time that the memory broadcast information to all the mechanism and update them. To do that, the model proposed in the paper used a new set of parameters again, and it shows them by the hat symbol. So for each of mechanism, it takes its updated representation, multiply it to a new set of parameters to form a new query. This query is gonna multiply to a key, which key indexed by J means that I take the slot J of memory, multiply it to another new set of parameters, see the hat here, and this notation E, which actually means the key. Then this multiplication here forms us the key transpose, and QK transpose again we see here like a scaling factor we have in transformers, and then the softmax gives us the scoring representation for the current mechanism over that slots of memory. We do that for every slots of memory. So index J here is actually shows the memory slots, and K is the same as previous slide, which is the mechanism number. So having this score, then we say that the current representation of each mechanism, either it wants be selected or not selected, no matter, because as you can see here, K goes for all of the mechanism. Now we are in step 3. As you remember, I explained in the previous slide that in step 3 the memory or shared memory is gonna update all the mechanism, no matter it is selected or not selected. So the new stage for each mechanism would be its current stage plus this summation, which is the scoring calculated here times 2V. So actually it just split down the Q, another set of QK transpose V. So instead of putting V here, it actually open it as a summation here, but it's the same actually. And V again comes from the transformer of the dot product between memory slots and another new set of parameters. So here this one, and this one are all new set of parameters. So this strategy actually all the mechanisms are updated. Okay, in this slide we talk about the most important experiments provided by the paper. The first one is equilateral triangle task. The task is this: given an image like this, is this points here form a triangle, equilateral triangle or not? The first row are all equilateral, by the second row they are not equilateral. So they apply their method on this task and compared with several other methods that explained here. And their method is this one and this one, like transformers plus shared workspace. The first S here means the soft version of shared workspace. The H here means that the hard version. The difference between soft and hard is that in hard they use top K strategy. They always use the top K mechanisms, but in soft they actually use all of them by with different weights. So as you can see, the hard version gets a better result compared to others. In second experiment, the model is given by an image with two types of question. The first question is the first set of questions. Actually, they are non-relational question. It means that this question, you can answer this question by only looking the specific object in the picture. For example, the question here is that what is the shape of the red object? So to answer this question, I just need to look at the red object. I don't need to know about other objects. But in relational questions, you need actually to find a relation between the objects. For example, here it says that how many objects have the same shape as the green object. So you need first to find the green object, guess its shape, and then look for other object if they follow the same shape here. So the shape of green object is the relation that you can find between others. And they get actually a better accuracy when they answer only the relational questions, which you can see they reach to a top of 80% of accuracy when they go for a hard version of shared workspace. And but in terms of non-relational questions, actually they can see all other methods, like most of them, like the green one and the brown one, they could reach to the same performance at the end. The good point about this model is that it actually converge a bit faster to get the results. So just following the blue one, you can see it converge a bit faster. They also did an ablation study by the brown, like darker brown one, this one. This one is like they apply in each state of transformer, they apply two set of self-attention. Like the second set up happens on top of the first one. They did this ablation study to make sure that their idea about shared workspace is not like applying two set of self-attention, and it shows that their idea is actually not like that. In this slide, we want to talk about the limitation and advantages of this model. Actually, this model is good for those sort of problems that we need to find a relation between the objects inside of the data to solve the task. For example, in uh, example of triangles, equilateral triangles, this model works better because there is some relation inside of the data. So also this model is good and provide a better at convergence rate in relational tasks. Like not only the accuracy gets better, but also the convergence rate is better. Finally, this model actually is a good effort to bring the idea of global workspace theory into the concept of deep learning. Like this is another step towards system to machine learning, or actually artificial general intelligence idea. And it tries to find a coordination between the submodules, which sounds like more close to idea of brain, human brain. And it is actually a good effort toward this concept. Actually, there are some limitations for this model. The first one is that this model works for certain tasks. Like we applied over Cipher 10, but for Cipher 10, because there was not much relation inside of the component of the image, so it was not that much good or that much significant different from other tasks. So actually, the target of this model is some specific tasks. Another limitation of this model that we found, and it is very important, is that the number of parameters by this model goes very high, and it is actually make it interactable or hard to apply for larger models. Like for example, we tested or a simple transformer that has 800k parameters, and then we apply shared workspace memory on this model, and it goes to 4 million, which is like many times bigger than the ordinary one. So this model, this paper is not scalable. We actually tried to provide some solutions for one of the limitation of this work. Like we suggest actually to tackle the problem of a large number of parameters this model use. We actually suggest a solution through providing a low rank representation for memory. Like memory doesn't need to be so big. We can force and limit memory to be low rank, because this way we get two advantage. First, the number of parameters drops down by at least 50%. Second, putting more pressure and limitation over memory force memory to actually capture the most important relation, and this way memory works much more efficient and find the relational objects and relations between objects much better. So what does that mean? It means that instead of using m by p by q, which is the size of m, the memory, we use two matrices A and B, like the multiplication of A and then B, which A is P by R and B is R by Q, and R is much smaller. So overall P in original M we have the number of parameters PQ, but in our suggestion, like AB, low rank representation of M, we have P by R plus R by Q. And because R is much lower than P and Q, then this number of parameters in this setting is much lower. We could achieve a minimum reduction of at least 50%, and also at the same time we could increase the performance by 5%, and this is really good. And actually, and the improvement we had over the paper is significant. We plan actually to further continue our idea for some NLP tasks, and then see how well this improvement, this idea can work in other uh, tasks like natural language processing. And thank you so much. This is our presentation, and the references we have are here. So thank you.